Hello everyone, this is lecture 1 of ComSci 142, Introduction to Algorithms. In today's video, we will discuss an algorithm for the stable marriage problem. Let's start with a scenario that involves internships. Let's say that Ross is currently an intern at Facebook, but Google calls Ross for an open intern slot at their company. Upon thinking about it, Ross actually wants to go to Google, then stay at Facebook. So he leaves Facebook and goes to Google. Now, Facebook is down one intern, so they call Chandler. And Chandler, who's currently at Amazon, actually wants to go to Facebook, then stay at Amazon. So Chandler leaves Amazon and goes to Facebook. Now this could get ugly real quick because there could be jealousy and other things, right? So for example, Phoebe, who's currently at Amazon, heard of Ross's internship at Google. Now Phoebe actually wants to go to Google, so she calls Google, and upon hearing this, Google determined that they actually want Phoebe more than Ross, and so they cancel their internship for Ross and give it to Phoebe. So it could get ugly, right? So this could turn into a cycle where things spiral out of control and there could be chaos and drama all around because the people and the company's own self-interest risks breaking existing relationships. Okay, so if they want to go to some other company or a company wants to hire another intern, they could do so and they would just break off existing relationships, right? And people could end up unhappy with the process and the outcome because they've already agreed to be an intern at this company and then suddenly it just gets broken off, right? So people end up unhappy. But there could also be stable situations. Like for example, Joey applies to Facebook, but Facebook is happy with their current interns. And so Facebook declines and Joey is not accepted. Or it could also be that Amazon reaches out to Monica, but Monica is already happy with her current company, and so Monica could also decline the offer from Amazon, right? So in these scenarios, the own self-interest of people prevents offers from being retracted and redirected because they are happy with their current situation. Okay, unlike in the previous scenario wherein their own self-interest allows breaking off of relationships. Okay, so in 1962, this type of situation was studied by David Gale and Gale-Shapley. Okay, they asked, could one design a college admissions process or a job recruiting process that was self-imposing? What does self-imposing mean? Okay, so specifically, this was their question. Given a set of preferences among employers and applicants, can we assign applicants to employers such that for each employer E and for each applicant A who's not employed at E, either the employer prefers every one of its accepted applicants over A, and A prefers his current employer over E. So what that means is that all employers are happy with their current applicants over others, and all applicants are happy with their current employers over other companies. Okay, and if this holds, the assignment of applicants to employers is stable, and that means that individual self-interests will prevent any applicants or employers from making a deal behind the scenes. So this is what they meant by self-imposing, that the own self-interest of people and companies will prevent them from doing backdoor transactions, like pirating people and moving over to other companies, right? So because they don't want to move already. Okay, they're happy with where they are currently. So that was their question. However, this scenario has a lot of asymmetries, okay, imbalances. Like for example, an applicant only needs to go to one company, but the company needs more than one applicant, right? Or the number of applicants may not be equal to the number of slots. So there could be 5 applicants, but there are only 3 slots, right? So it's also imbalanced. And typically, an applicant doesn't really need to apply to all companies as well. So there's this asymmetry that makes it a little bit more complicated as a problem. And so what they did was they wanted to make the problem as simple as possible. So they made a bare bones version of the problem. So they tried to remove those asymmetries because they were just distracting, and they wanted to focus on the fundamental issue of the problem. And they discovered later on that even the bare bones solution extends to the general version as well. So it was okay for them to study the bare bones version and use that solution to for the general version of the problem. So the bare bones version of this problem goes like this. Each of the n applicants, so let's say that there are n applicants, each of the n applicants apply to each of the n companies. So let's say that there are 3 applicants and 3 companies. So all applicants applies to all companies, just to make it simple, without the asymmetry that applicants could choose not to apply to some companies, right? So in the bare bones version, just apply to all companies. And each company will also accept only one applicant. So 1:1 siya. Okay? And they found out that this bare bones version, Gale and Shapley observed that this can be viewed as, instead of applicants and companies, there could be n men and n women getting married. Okay? Getting paired up in marriage. So everyone is seeking to be paired with exactly one individual of the opposite sex. Okay? Because one company is accepting one applicant, so that's similar to how one woman would accept one man in marriage, right? So that is how the stable marriage problem was formulated. Okay? Now, before we go further, let's define some things. So first, we define matching. So what is a matching? A matching is a set of ordered pairs where each man and woman appears in at most one pair. So given a list of men and women, a matching is where a pairing of men and women where each one of them appears in at most one pair. And when we say at most one, it could be 1 or 0. So, pwede siya mag-appear sa pair, pwede rin hindi. Okay? They could appear or not appear in that pair. Next is called the perfect matching. Now, in a perfect matching, it's a matching where each man and woman appears in exactly one pair. So, earlier in a matching, we said at most 1. So, it could be 0, it could be 1. In a perfect match, everyone has to be in exactly one pair. So everyone is married in this case. Nobody is single, nobody is polygamous. So no one is left behind and no one has more than one pair also. So exactly one pair lang. Okay? Now, we also have this concept of preferences. Okay? Man will rank all women according to their preference and vice versa. So women will also rank the men according to their preference. So the ranking indicates that if this woman is number 1 on my list, I prefer to be paired with her. And then kung sa last siya, that's the least that I prefer. Okay? Higher rank means more preferable, as I mentioned. And it's important that the preference list should have no ties. Okay, so you really have to rank all of them. Okay, now what can go wrong in this scenario? Let's say that the matching has pairs M1 and W1 and M2 W2. So the M's are men, the W's are women. So man 1, woman 1 are paired up, man 2, woman 2 are paired up. But for man 1, he actually prefers woman 2 than woman 1. And for woman 2, he actually prefers man 1 over man 2. So what is the problem here? The problem is that since man 1 prefers woman 2, who is not his current partner, and woman 2 also prefers man 1, who is not her current partner, they can both abandon their current partners and pair up, and they will both be happier, right? Because they prefer each other. And so these types of things are called instabilities. Okay? So the M1W2 pair does not belong in the matching, but if they do pair up because they prefer each other compared to their current partners, it will break the current matching. Okay, so it becomes unstable. So that is an instability. It's like the anay that breaks the world of the married, right? So our goal, therefore, is to find a matching that has no instabilities, because it could get ugly if there is such a thing, right? Now, what's stopping man 1 and woman 2 from like running off into the sunset with each other and leaving their current partners behind? So of course, in this scenario, woman 1 and man 2 would become sad and they won't be happy anymore, right? Yeah, so that's the goal, no? To find a stable matching. Okay, so a matching is stable if, number one, it's a perfect matching, so everyone has to be paired up to someone, everyone is married, and number two, it has no instabilities, so there are no pairs, no possible pairs that could, let's say, pair up and destroy other matchings. Okay, so no instabilities. Now, question: does there exist a stable matching for every set of preference list? So given n men, n women, they rank each other, they have their own preference lists, will there always be a stable matching for that one? And if one exists, given their preferences, can we efficiently construct a stable matching if it does exist, right? So is there an algorithm for it? And okay, let's see. No, so let's have an example for this one. Okay, so let's say that we have two men and two women. So Eric and Michael are the men, Donna and Jackie are the women. And for Eric, he prefers Donna over Jackie, and Michael prefers Jackie over Donna. For Donna, she prefers Eric over Michael, and for Jackie, she prefers Michael over Eric. And so this is actually an example wherein everything is in what do you call this, like in harmony, right? Because Eric and Michael prefer different women, and the same with the women, they prefer different men, so there are no crossing of paths. So what are the perfect matchings for this example? So remember that a perfect match just is a list of pairings in such that everyone is paired up. So there are actually two perfect matches here. The first one is when Eric and Donna are paired up and Michael and Jackie are paired up. So this is one perfect match because all the men and all the women are in a pair. The other perfect match is when we pair Eric and Jackie and Michael with Donna. Okay, so that is also a perfect match because all four of them are part of the pairing. Okay, now the next question is, are these stable? Okay, this matching is actually stable. Yes, because Eric actually does prefer Donna here over Jackie. So Eric is happy with Donna, right? And how about Donna? Donna prefers Eric over Michael. So Donna is also happy with Eric. And then for Michael, he prefers Jackie over Donna. So Michael is also happy being paired with Jackie. And same with Jackie, who prefers Michael over Eric. Okay, so everyone is happy in this scenario, right? So this is a stable matching. But how about the second perfect match? Is it stable? This one is actually not stable because there is an instability. Now, what is the instability here? The instability is the pair of Eric and Donna. So that is one instability. Because why is this an instability? So remember that an instability is a pair that does not exist in your matching, but it could break this matching. And why would this break the matching? Because Eric actually would prefer Donna over Jackie, right? And same with Donna. Donna prefers Eric over Michael. Okay? So it has to be both ways, by the way, the instability. If Eric likes Donna more than Jackie, but Donna is content with Michael over Eric, then it's not an instability. Okay? It's only an instability if they both like each other over their current partners. If it's one-sided, then it's not an instability. Okay? Because one side is already content with who he or she has currently as a partner. Okay? So this one is not a stable match, but it is a perfect match. Okay? There is an instability here. Okay. So that's the first example. So yeah, this is just pointing out the examples that we saw earlier. It's not stable because there is an instability. Okay? Now let's see another example. This time we have Ross and Joey as the male, or the men, and Rachel and Phoebe as the women. And for Ross, he prefers Rachel over Phoebe, and for Joey, prefers Phoebe over Rachel. And then for Rachel, prefers Joey over Ross. Phoebe prefers Ross over Joey. Now you'll notice that for the men, they're actually also in harmony because they prefer different women. And then the same for women also. They're also in harmony because they prefer different men. However, the cross liking of each other does not really mesh well, unlike in the first example. Because if you look at this, Ross prefers Rachel, right? But, so, Ross prefers Rachel, but Rachel prefers Joey. And Joey prefers Phoebe, right? And Phoebe prefers Ross. So they actually like someone else who likes someone else who likes someone else. Okay, so it's like a cycle. So let's see if they could still be happy. Okay, even with this scenario. So what are the perfect matches in this example? So again, it's just a pairing where everyone is part of a pair. So the perfect matches are, you could pair Ross with Rachel and Joey with Phoebe, right? Another perfect match is if you pair Ross with Phoebe and Joey with Rachel. Okay? Now, are these stable? For the first one, this is actually stable because there are no instabilities. Okay, now you might say, what could be a possible instability here? Ross and, let's say, Phoebe. Let's try if it's an instability. Now, Ross is content with Rachel because he actually prefers Rachel over Phoebe. So Ross will not be part of an instability, even if Phoebe prefers Ross over current partner Joey. So only Phoebe will be part of this, but Ross is content with Rachel. So it's not an instability. How about the other one? Joey and Rachel. Is that an instability for this perfect match? Joey prefers Phoebe over Rachel. So Joey will actually be content with Phoebe, even if Rachel wants Joey over Ross. So it's also not an instability. Okay? So this one is actually stable. And then the same thing for this perfect match. This is also stable because there is no instability. Now, for the other one, just use the opposite pairings here. But you'll find out that it's also not an instability because one party is content with who he or she has. Okay? Now, who is happy in these scenarios? In these pairings, you'll notice that the men are happy. Why is that? Because Ross got his girl, Rachel, and Joey got his preference, Phoebe. So the men are happy here, right? But in the second perfect match, it's the women who are happy. Why is that? Because Phoebe got her preference, which is Ross here, and Rachel got her preference, which is Joey here. So in this scenario, both women are happy. Okay? So it's possible to have more than one stable match, and it depends which side becomes happy in these scenarios. Okay? So yeah. So this is from the previous slide. So both are stable matchings. So it's possible to have more than one stable match. And in the first stable match, both men are happy. In the second one, both women are happy. Okay? Now, okay. So now that we've seen examples, how will we go about creating a stable marriage given the list of preferences? So how will we do the algorithm? Okay, so the idea is that initially everyone is free. Okay, everyone is single, no pairs yet. Now, let me ask you this. If a free man, so meaning a single man, proposes to a woman who ranks highest in his preference, because obviously the man would want to propose first to the one high in his preference list, right? The one that he wants the most. Can we already declare that M and W are one of the pairs in the final stable match? Final na ba na M and W are part of the stable matching if M proposes to W? Well, not necessarily, right? Things could change, okay? Because there could be some other man, M2, who could propose to the woman W in the future, and the woman actually likes M2 better than the current man M. Okay, so it doesn't mean that when M proposes to W, sila na. Okay, in the end, because remember, walang forever, right? But you know, so things could change, right? Now, on the other hand, if the woman W receives a proposal from a man M, but he ranks really low on her preference, like maybe dead last or second to the last, should she reject that proposal also? Okay, just because maybe I don't really want him as my partner, so maybe I should just reject his proposal. Well, it's also dangerous if the woman rejects the man right away. Why is that? Because the woman is not assured of receiving a future proposal from someone who ranks higher than M. Okay, maybe the woman would reject the man because she's hoping that someone else better will come along, but she's not assured of that. Maybe the other guys are not into her. Okay, maybe the other guys also prefer other women, and so if she rejects the man right away, then maybe she'll be left alone if no one else proposes to her, so she'll remain single. Okay, so it's not safe to reject right away. Okay, so the solution for this is don't marry right away. Go to engagement first. Okay, so be engaged first, and while you're engaged, women can still entertain other men's proposals because it's not yet final anyway, right? So things could still change. So the women can still listen to other proposals from other men, and if that does happen, so there will be a love triangle, right? So the woman can just choose the man she prefers, right? Because, well, I like this man better, so I'll go to him. Okay, so again, everyone is single at first. If a man proposes to a woman, they should be engaged, not married right away. Engaged lang. The woman should not reject right away if she's free, because she might not get another proposal that's better, right? So it's also not safe to reject. So just accept it for now, and if better offers come along later, then you can move to better men. If not, then you're stuck with this guy. Okay, so that's the basic idea of the algorithm. Okay, so putting all of those together, this is the Gale-Shapley algorithm. Okay, so initially all men and women are free, and this is the main while loop. Okay, so while there's a man M who is free and has not proposed to every woman, so that means that he's single and he hasn't proposed to all women yet. So let W be the highest ranked woman in M's preference list that he hasn't proposed to yet. So meaning, so at first, that man will propose to rank number 1 woman. So number 1 woman. Now if he's rejected, then he will go to number 2, and then if rejected, go to number 3, and so on. Okay, so the highest ranked woman in his preference list that he hasn't proposed to yet. Now, there are 2 instances. It could be that the woman is free, so also single. So if that's the case, they would be engaged. Okay, because it would be dangerous for a woman to reject the proposal. But if W is not free and is currently engaged to fiancé F, then the woman would have to choose. If she prefers F over M, then M will be rejected and he'll remain free. But if W actually prefers M over the fiancé F, then the engagement of F and W would be broken, and F would become free. And then M and W would get engaged. Okay? So the loser basically of the love triangle will become free, and whoever is more preferred gets engaged with the woman. Okay? So this will happen until everyone is engaged, and return the set of engaged pairs as the final stable matching or the stable marriage. Okay? So that is how the Gale-Shapley algorithm works. Okay, so let's see a little demo of Gale-Shapley algorithm. So I asked some of your classmates to volunteer. So it's not really volunteering if I handpick them. But anyway, so I asked 5 men and 5 women to send their preferences. So it's here. Now I've converted this into code names so that their privacies are also protected. So we have 5 men. We have Brian, John, Julian, Rick, and Zorro. And the 5 women, si Baby Girl, Emilia, Ivy, Maria, and Marites. So these are their preferences, which we will consult later. Okay, so first we have Rick, who is free. Rick will choose Emilia because that's the top of his priority. So since Emilia is still free, they will get engaged. So Rick and Emilia are engaged. Okay, next we have Brian, who will propose to Marites because that's the top of his list. And since Marites is free, they will also get engaged. Okay, so there are now 2 pairs currently. Next, si Julian, the top of his priority list is Baby Girl, and since Baby Girl is free, they will also get engaged. Okay, so there are now 2 remaining na lang. Next is si Zorro, and Zorro's preference is also Baby Girl, ang number 1 niya. But Baby Girl is already currently engaged to Julian. So Baby Girl will choose between Julian and Zorro. But it turns out Julian is higher on the preference list. So Zorro will get declined. Okay, sorry Zorro. Okay, so Baby Girl will remain with Julian, and Zorro will remain free. So ang next, si John, who is also free, will also try with Baby Girl because that's also his highest preference. And so again, ma-choose si Baby Girl between current partner Julian and John. But it turns out Julian is the top pick of Baby Girl, so John will remain free, and he'll get declined. Okay, so sorry si John. Okay, next. So si Zorro again ang propose. So wait. Okay, so we're now here. So Zorro will propose now to the next in his list, which is Emilia. And Emilia, who is currently engaged to Rick, will pick between Zorro and Rick. But Rick is higher on her preference than Zorro, so Zorro will again be declined. Sorry. Okay. Now, next for Zorro, he'll choose Ivy. Okay. And since Ivy is currently free, so they will get engaged. Okay. So the only free now is si John na lang. Now, John will go to his next pick, who's Emilia. And so Emilia will have to choose between John and Rick. And John is actually higher on the list than Rick. So, si Rick ang maging free. Okay? So, ma-break off ang engagement nila, and si John ang maging engaged kay Rick. Does that make sense? Okay? So now, si Rick naman ang free. And so Rick will go to the next girl, which is baby girl, but again, he cannot beat Julian, which is baby girl's first pick, and so he moves on to the next. He chooses Marites, who's currently with Brian, and so Marites will choose between Rick and Brian, but Rick is actually the first choice of Marites. So Brian will become free, and Rick and Marites gets engaged. Okay? And then so si Brian naman ang free. Then Brian goes to Emilia, but Emilia, who's currently with John, prefers John over Brian, who's actually his last pick. So Brian cannot beat John. Brian tries baby girl, but again he cannot defeat si Julian. Brian tries Ivy, also declined because Ivy, who is currently with Zorro. So Zorro versus Brian kay Ivy. Zorro wins because Zorro is the first pick of Ivy. Okay? And so Brian is declined again, and so wala na choice si Brian. He goes to Maria, which is his last pick supposedly, but he has no choice, right? So Brian and Maria are engaged because Maria is free, and that is now your final set of pairs. So you have Brian and Maria, John and Emilia, Julian and baby girl, Rick and Marites, Zorro and Ivy. Okay? So that's an example of your Gale-Shapley algorithm in action. And let's see if there are their preferences. So for their preferences, you'll notice that for the men, like these three men in particular, they kind of have similar preferences, right? So baby girl, Emilia, Ivy are more or less their top 3 or top 4, and then these two have slightly different preferences. But sa girls, you can see that it's mostly mixed up, right? So it's not a uniform preference, but it's mixed preferences. And so Brian actually, for Brian, he ended up with his last choice, which is Maria. And for Maria, Brian was his third choice. Okay? Because if you remember, Brian tried everyone, but everyone was happy with who they have currently. For John, he settled with his second pick, Emilia, and Emilia, John was her second pick also. So they're happy with each other even if they were only the second picks. And for Julian and baby girl, they were actually each other's first picks. So Julian, baby girl lang malakas. There's no beating them because they are each other's first picks. So no matter who proposed to baby girl, they could not beat Julian because he was already the first pick, right? For Rick, Marites was his third choice. For Marites, Rick was the first choice. So Marites is happy in this scenario. And lastly, Zorro had Ivy as her third choice, but Ivy also had Zorro as her first choice. So in this case, Ivy is happy. Okay, so that's it. We'll return to this example later, but that's basically the demo for Gale-Shapley algorithm. Yeah. Okay. So now let's try to analyze the algorithm. um, it's not immediately obvious that the algorithm returns a perfect matching, right? Or even a stable matching in that case. So it's not immediately obvious. So let's see if they do indeed, if it does indeed return a stable matching. Sorry. So let's see some facts. Fact number one: a woman W remains engaged from the point she first receives a proposal, and the sequence of partners she is engaged to gets better in terms of her preference. So this is true because remember that a woman starts off being single, and whenever someone proposes to her, she accepts that proposal and she gets engaged. And from then on, she never becomes single because she will just accept a proposal if it's better. Otherwise, she'll stay engaged with whoever she currently has. Okay? So, the sequence of partners she is engaged to gets better because she will only change if she prefers that guy over the current partner. So, this is true. Fact number two: the sequence of women to whom a man proposes to gets worse in terms of his preference. This is also true. Okay, sorry. Okay, so again, the sequence of women to whom a man proposes to gets worse in terms of his preference. This is true because the man starts off with the highest in his preference list, and when he gets declined or he gets replaced by someone better, he will go to the next in his list until he gets to the bottom of his list uh, eventually. Okay, so it gets worse in terms of his preference. Number 3. The Gale-Shapley algorithm terminates after at most n squared iterations of the while loop. This is also true because how many possible pairs are there for n men and n women? So there are at most n squared pairs, right? So n, if there are n men and n women, so from discrete math, we'll have n squared pairs. So since there are at most n squared pairs possible, it would have at most n squared iterations of the while loop also. Okay, and in that case, it's already going through all possible pairs, right? So usually it's not really n squared, it's just an upper bound. Okay, it terminates way before it reaches n squared anyway. Okay, now how do we show that before we can show that it's a stable match, we have to first show that it's a perfect match, right? Because a stable matching is a perfect matching with no instabilities. So we have to show that at the end of the run, all men and women have partners. Okay, so show that no man can fall off the end of his preference list and still be single. That means that he has already proposed to everyone, every woman, and he's still single. So that can't happen. Okay, so the idea is that the loop only exits if there is no free man, right? So no single man, and that means that all men are engaged for the loop to exit. And if all men are engaged, since there are n men, that means that there are also n women that are engaged. So n men and n women engaged means that there is a perfect matching. Okay, so that's the basic idea of it. Now, for facts number 4 to 6, there are proofs for these facts, but they are detailed in the lecture notes. So just read the proof by contradiction in the lecture notes for the proof of these facts. But I'll just explain the basic idea behind the reasoning. Okay? So fact number 4, if man M is free at some point, then there is a woman to whom he hasn't proposed to yet. Okay, The reason for this is because if he is free at some point, that means that there's still someone that you haven't tried yet because you're still single, right? And you can't have proposed to everyone and still be single, because if a woman gets proposed to, she does not decline unless she's already engaged, right? So if you're still single at some point in the loop, then you can still propose to someone else. The set of pairs returned at the termination of the algorithm is a perfect matching because everyone will be paired up. And lastly, the set of pairs returned at the termination of the algorithm is a stable matching, so there are no instabilities. And again, for fact number 5 and 6, the proof of this would be available in the lecture notes. So just read the lecture notes for the details of the proof. Okay? Now, recall earlier in example number 2, we saw that there could be two possible stable matchings. So this one was where both men are happy, and this one was where both women were happy. So which stable matching would the Gale-Shapley algorithm produce? Okay, so the Gale-Shapley algorithm can only produce the first stable matching where there are happy men. The second stable matching, when there is happy women, is only attainable if the women propose, if we change things up and let women propose instead of the men. Okay, so we kind of see the unfairness of Gale-Shapley algorithm. So it kind of favors men, or technically the one who does the proposing. Okay, so some people are bound to end up unhappy because of this. Okay, so if men propose, women are unhappy. If women propose, men are unhappy. Okay, so why is that? It's because it's because whoever is not proposing is just waiting for the best possible proposal to come, right? So they really have no choice but to wait. Okay, so some of them end up unhappy. Now, regarding order, the algorithm is actually underspecified. It doesn't tell us which man proposes next. Okay, so it could just be any random man who is free and single, right? So it doesn't signify order. So if there are different orders of men proposing, there could be different executions of the algorithm, right? Because a different ordering, like what if A goes before B and then C, but what if B proposed before A and then C follows, or C goes first and then A and then B? So that could be a different execution of the algorithm, right? And could there be a different result or a different stable matching? Okay, so we could question that, right? Do all executions of the Gale-Shapley algorithm yield the same matching if the order is arbitrary? So is the order of men proposals relevant? Does it change does the order change the result? Well, it turns out all executions yield the same matching. So no matter what the order of men proposing would be, it would yield the same stable matching. So once the preference lists are already finalized, then there's only one answer that's left to be discovered. Okay, so that's already set in stone once you have given your preference list. Okay, there's already one stable matching that would be produced by the algorithm regardless of the order of proposals. Okay, so the matching produced by Gale-Shapley algorithm is the one where each man ends up with his best valid partner. Okay, now what does this mean? So to define best valid partner, let's define a valid partner first. So W, or the woman W, is a valid partner of M if there's a stable matching that contains MW. So, valid partner siya if they belong in a stable matching. The best valid partner is if first, valid partner siya, and all women ranked higher than W on M's preference cannot be M's valid partner. Okay, so what does this mean? Okay, so let's say that we have a man here, and the women that she prefers are A, B, and C. And let's say that man M is paired up with C. So if C is his best valid partner, that means that M cannot be paired with A, M cannot be paired with B in a stable matching. That means that maybe A prefers the current partner over M, same with B. Okay, so even if M wants A better, A does not want M over maybe partner N or O in this case. Okay, even if he wants these two women better, they don't want him more than their current partners. So the best that he could do is C at this point. And now there could also be worse women in his preference list, right? So that's the concept of best valid partner. Okay, it's not your most preferred woman, but the best that you could do given the circumstances. And then the worst valid partner naman is the opposite. Okay, it's the valid partner, and this is for women. Okay, so all men ranked lower than M on W's preference cannot be W's valid partner. Okay, so it's just the same thing, but only this time it's worse. Okay, so okay, so it's on the opposite side naman. So let's say the woman has preference B, C, D, then A, and then let's say that W is paired with B. Now, these are men, by the way. There are worse men on her preference list, but in this case they cannot be paired because maybe they prefer their current partners over with woman W. Okay, so this is the worst that she could do given the circumstance. Okay, so the last two facts indicate that every execution of the algorithm returns the matching where each man ends up with his best valid partner, and that means that all executions of the algorithm returns the same matching because it's the one with all best valid partners for the men. So it's the same matching. Okay, so that means that the order of men proposals don't affect the outcome. Okay, and the algorithm always results in the best possible outcome for every man, and no other stable matching exists where any man could have had a better partner. Okay, and the last fact is that in the stable matching returned by the algorithm, each woman is paired with her worst valid partner. Okay, so it's not really ideal for women or those who are not proposing. Okay, so for any set of preferences in general, those who propose get the best possible stable matching, and those who receive proposals get the worst possible stable matching. Okay, so that's it. Let's see this in the demo again. Okay, so I'll show you some code, a little bit of code. Now, when I run this one in the first time, there's still a random seed, so it will run the same each time. So it's always Rick, Emilia, Brian, Marites each time, right? So it has a fixed order. But if I remove this random seed, then it will be randomized each time. Okay, so let's see. So this time it's John baby girl, Julian baby girl, that one. Okay, so this is the order. And you'll notice that the results were still Brian Maria, John Emilia, Julian baby girl, Rick Marites, Zorro Ivy. It's still the same. Okay, so let's copy this, and that's our first one. Now let's run it again. This time it has a different order, right? So John baby girl, Brian Marites naman, but the results eventually are still the same. So if I copy this here, it's still the same result. So the first one was John baby girl, Brian Marites. Let's run it one more time. This time it's Rick, Emilia, Brian, Marites, and it's still the same results. Okay, so no matter the order, what the order of the proposals are, doesn't matter, because it will eventually lead to the same result here. Okay, so yeah, that's it. What else? Yeah, okay, so that's it. And okay, so that's it for this video. And if you have any questions, don't hesitate to ask me in Messenger, in the group chat, and I will see you next time.